Alright, so now I'm back to my old self. What was I up to before we started talking about stress and strain? Is that Steelio? I should refer back to my learning objectives. Oh yes, we were just talking about, we know how to define and explain engineering stress and strain, but now we want to be able to draw a typical stress-strain curve for a ductile metal and describe the different regions. And it seems like we can use that uniaxial tension test. That's what I was doing. I was all set to do a test. Well, if I'm going to do a lab test, I better get all kinds of prepared. Let me get my lab coat back on. I know it's overkill, but it looks so good, don't you think? And for sure, I need to get my glasses on. Alright, ready to go. Now I need to find something to test, to put in our uniaxial tension test machine. What's that, Steelio? No, I couldn't ask you to do that. Class, it's so generous of Steelio. Steelio offered to be put into a uniaxial test, universal testing machine and have the uniaxial tension test performed on him. Oh my God, I don't know if I can let you do it. I can? Okay. Well, if we're going to test Steelio, we have to get some initial measurements first. So, I'm going to go ahead and grab my calipers and I need to get some initial dimensions. So we're going to firstly need the diameter of Steelio, this reduced diameter. Alright, so I'll go ahead, perform my measurements. I'm in millimeters here. And it looks like if I do my measurements correctly, we get about 9.55 millimeters for our initial diameter. So you can go ahead on page 3 of your notes and add this dimension, right? So you should have something that looks similar to this, some sort of test data sheet. And in our initial geometry, I want you to get down the initial diameter, 9.55 millimeters. Now you guys can do the area calculation. So that's going to be pi over 2 times the radius squared. So pi r squared over 2. Or if you work in the diameter, it's going to be pi over 4 times the diameter squared. So you can calculate the area. If you do those calculations for the area, you should get 71.636 millimeters squared. All right. That's good. We also need to not forget about the strain aspect, right? So the area helps us with stress. And for strain, we need to set an initial length. So sometimes you're going to have a direct measurement that you want to calculate. So, if you have a measurement device, you're going to set it up to be a certain distance. Here, I'm just going to pick 2 spots, and I'm going to just draw a little circle where those spots are. And I'm going to do it kind of across this mainly flat portion. And now I want to go ahead and I want to get the initial length of that. So this is going to be just the flat portion. So I go ahead and between my 2 dots, I take another measurement here. And it looks like my initial length, as I have it measured, is about 57.15 millimeters. So let's get those numbers into our notes. So I have this test data sheet for Steelio set up for you. So we want to get the measurements in for the initial geometry. So our initial diameter was 9.55 millimeters. Doing our area calculation, pi r squared or doing pi d0 squared over 4 gives us 71.636 millimeters squared. And lastly, we took our initial length and found it to be 57.15 millimeters. All right, we got the initial dimensions of Steelio. I think you're ready for the test. I got this cool software thing, advancements with computers and everything. It's very cool, right? So I'm just going to insert you into my computer here. See if I can get you into the testing machine. Here we go. Whoa, did you see that? Well, probably not. We got a very little amount of deflection, but our force went up pretty substantially, and you could tell that if you could see the pressure gauge there increase. We find that in the very initial portions, especially for ductile metal, we have what we call linear elastic behavior. So in this region, the stresses are directly proportional to the strains. Remember, stress can be derived from force divided by the initial area, and the strain will be the change in length over the initial length. What does it mean to be directly proportional? Well, directly proportional just means there's a linear relationship, or we can set up a relationship between stress and strain through the slope of the line. And the slope of that line is going to be capital E. That'll be what we call the modulus of elasticity, or also known as Young's modulus. So we will use those terms interchangeably to describe this proportionality between stress and strain. All right, we'll hop back to the test and see what happens next. So we're 24, 25 kilonewtons, 26, 27, 26.5, 26.6. Got some yielding going on. And so yielding is the second region of our stress-strain curve for a typical ductile metal. Yielding is characterized by an increase in deflection without an increase in force, or in other words, an increase in strain without an increase in stress. Now, the stress doesn't drop to zero, it's just remaining constant, and you could hear me kind of stagnate around 26, 26.5, 27 kilonewtons, and that was meaning that the force was remaining the same, even though I was continuing to pump the cylinder and stretch the material. This point is known as the yield stress, capital F sub y, and this is the stress at which the material starts to deform plastically. 27, 28, maybe some strain hardening. 29, 30, 32. Really see the stretch. 33, 34, 35. 6. Alright, so you can see I was working hard there to get through the third region of our stress-strain curve, which is called strain hardening. So you could hear that the forces started to increase again, maybe not as quickly as they did at the beginning, but they were continuing to increase. So strain hardening kind of represents the material having some sort of reserve strength. From a material perspective, what's happening in a ductile metal is that all the dislocations at the atomic level, all those dislocations are kind of shifting to the grain boundaries, and then at the grain boundaries they tangle, and it takes additional force to break those bonds to get additional movement in the material. So that's what strain hardening is. That's what it means by strain hardening. These dislocations tangle. We need extra force to keep stretching the material. And so ultimately, this will take us to the maximum amount of stress that the material can handle, which we call the ultimate tensile strength, or F sub U. It's really stretching now. 6, 6, 37, 37, 7, 7. Starting neck. The final region of our stress-strain curve is what we call necking. And necking is marked by a reduction in the cross-section. So you can see right in the middle of Steelio, the area is starting to rapidly reduce. And this is marked by a decrease in engineering stress, as well as we continue to strain the material. And that's enough of that. After this point, Steelio would just go on to finish necking, and we'll end up breaking. But we don't want to see that, right? What's that? You want to break Steelio? But why? Steelio's our friend. Because you want to learn about engineering and so we should break it? I guess that's a good point. Steelio, are you willing to sacrifice yourself? It seems so. I guess we'll continue. There. Going down and load. 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 Peak value is 36.94 kilonewtons. And hopefully you were able to keep up, but if not, pause it here and get down these notes. Oh, that was heartbreaking to watch. Poor Steelio. But we don't want his sacrifice to be in vain. So let's go ahead and retrieve Steelio from the tension test machine. Seems I got Steelio back out. He looks a little longer than he was initially. Let's go ahead and get our final length measurement. So those 2 dots we had originally, we now want to just take the specimen, see where it fractured, line it up so that the fractured surface is matching. We'll line that up, set it out on our table. Make sure it doesn't roll away on us. Then we'll take our calipers again and once again measure for the final length. This thing keeps rolling away. Alright, so come on. Measure between the 2 dots. Further here. Alright, it looks like our measurement is now 75.31 millimeters. So go ahead and put that into our test data. And as we jot down the final length of 75.31 millimeters, take a look at Steelio before and after the test to see the difference in stretch. Now you can go ahead and finish up that test data. We'll have to go back to the actual test to get some of the numbers. For our ultimate force, I think we heard from the ultimate force that the ultimate force we had was about 36,940 newtons. And we had our yield force was about 26,500 newtons. So I think I said those things there in the video. And so we can go ahead and convert that into stress and to find the yield stress, to find the ultimate stress, and then to find the total amount of strain and the percent elongation. So let's go ahead and work through those calculations. So let's wrap up the test data for Steelio. We heard from the video that the specimen yielded at 26.5 kilonewtons or 26,500 newtons, and then the ultimate force was 36,940 newtons. Okay, so as I ran the test, we had to kind of approximate this yield force, but the ultimate force was being measured by a device that was just recording the max force measured at any point during the test, so we were able to get more accurate there. I want to take advantage of the units here. Units 1 Newton per millimeter squared is a megapascal. It's also 1 million newtons per meter squared is a megapascal. So doing my math here for the yield stress, I take the yield force, 26,500 newtons, divided by 71.636 millimeters squared, and I get a yield stress of 370 megapascals. Likewise, I can calculate the ultimate stress by taking 36,940 newtons, dividing it by 71.636 millimeters squared, and I get 516 megapascals. Finally, I want to look at the percent elongation. So first I have to calculate the strain at fracture. So I'm going to take my final length minus my initial length and divide it by my initial length. Remember, strain is delta L over L0. This gives me a value of 0.317760, And this value is unitless because it's inches divided by inches. That's why sometimes it's easier to think about strain as maybe the percent elongation. If we multiply this number by 100%, we see that the percent elongation was about 31.78%. So that means Steelio stretched from its initial length, it increased in length by 31.78%. Finally, if you have trouble working with the SI unit system or having a physical feel, I'm going to switch these and just kind of write them in brackets as in the US customary unit system. So 26,500 newtons is about 5.96 kips or 5,960 pounds. And 370 megapascals is then 53.7 kips per square inch. So the steel can hold 53,700 pounds for every square inch of material it has. And that's just to the yield stress. Then when we look at the ultimate stress, it can go up to 74,800 pounds per square inch or 74.8 KSI. This is a typical value for a steel that we would build buildings with or fabricate parts with. So hopefully it gives you an idea for the amount of force or the amount of stress and the amount of strain, the amount of stretch that steel can undergo, a typical steel can undergo before failure. All right, so I think that will give us our start on doing some calculations with stress and strain. I look forward to the next video. We're going to take a look at some of the other engineering properties that we can gain from the stress-strain curve.